Good evening, everybody, and welcome to the Wheeler Centre. I'm Vanessa Taholka, and I'm delighted that you could all join us this evening for The Future is Fungal. I would like to acknowledge that we're meeting today on the traditional lands of the Kulin Nation and pay my respects to their elders past, present and emerging, and pay my respects to the elders of any other communities who may be with us today. The Wheeler Centre would like to extend a warm thanks to their event partner, Womadelaide Planet Talks program. Our guest speakers tonight are Dr. Brian Pickles and Gavin McIntyre. Brian is one of the lead researchers of the University of British Columbia's Mother Tree project alongside Suzanne Simard. You might have seen their work on a TED Talk recently. Their groundbreaking research has found that trees communicate with each other. Brian thought he'd grow up to be a fighter pilot or an astrophysicist, but got dengue fever and became an ecologist with a PhD in plant science, not necessarily in that order. With a dual degree in mechanical engineering and product design, Gavin is the co-founder, chief scientist and director of business development of Ecovative. I should have checked this backstage. I knew I forgot one thing. Ecovative?
Ecovative.
Ecovative.
It's a challenge when you invent a word as
We'll
well.
focus on the Ecovative. I love it. Ecovative is a biomaterials company that leverages fungal mycelium to create disruptive solutions for our planet's most pressing problems. Gavin co-invented the MycoBond platform, a patent-pending technology at the time, that uses a growing organism to transform agricultural byproducts into strong composite materials, and he continues to invent and innovate in the biotech space. This evening, they are going to share how their research and inventions in mycology technology are solving problems in new ways. Following the discussion, there will be a chance to ask some questions, so keep that in mind as your curiosity gets piqued throughout this chat. Please join me now in welcoming Dr. Brian Pickles and Gavin McIntyre. So to kick off, let's explore some of the key inventions and discoveries that you've both made. Brian, our audience might know you from the Mother Tree project already, but plenty of people will not have read those papers or seen that TED Talk quite yet. Your research found that trees communicate with each other and can share nutrients. Can you tell us a bit about that research and its significance?
Sure. So the system that I work in is mainly mycorrhizal fungi. Now, plants and fungi have been interacting with each other for, well, over 400 million years, pretty much since plants came onto land. Fungi have been interacting with them, and they've been transferring signals back and forth to each other using various different proteins, protein kinases, they're passing information to each other. The trees that I work on form this ectomycorrhizal symbiosis. That's mainly what I'm working in. And that only represents about 5% of the known plant kingdom. But the fungi that are interacting with these plants, those plants represent most of the big trees that you see in ecosystems. So your eucalypts here, Douglas fir, which is what I mainly work with in Canada, all of the Pinaceae. And essentially what's happening is plant roots aren't actually that great at extracting nutrients from the soil. What they do is they form a symbiotic association with fungi. Fungi are an order of magnitude or more smaller than the plant roots, so they're very able to move out into the soil matrix and extract water and nutrients from the soil. So essentially, when a plant is growing and putting out new root tips, it will transfer some signals into the soil, essentially saying, I'm looking for mutualists. And a fungus will say, it'll send out some proteins into the soil saying, I'm a mutualist, please turn off your defenses, don't kill me. And then the fungus will interact with the plant. They will form this joint organ, the mycorrhiza, which means plant root. And the fungus will extract water and nutrients from the soil, provide protection from pathogens for the root tip, and in exchange it gets sugar from the plant, which the plant has produced through photosynthesis. And these associations are ancient. We find evidence of them in the fossil record going back, I think the Rhynie chert from Aberdeenshire, which is where I'm from, has some of the first fossil evidence of these from about 407 million years ago. So they've been around for quite a long time, doing their thing, collecting all these nutrients from the soil and transferring them to trees. Now, the really cool thing about these fungi is that you can have one fungus that extends out, joining multiple plant roots, not just within the same plant, but between two or more plants, and not just between plants of the same species, but some of these fungi can actually link up multiple species together. And so there are all these pathways in the soil, which is where the idea of the Wood Wide Web has come from. Yeah, it's pretty good, isn't it? It's pretty evocative. So you've got all these connections going on in the soil, connecting up plants and fungi collecting nutrients from the environment. So lots of potential pathways for things to move around, and the fungi and plants are all producing these chemicals, which is how they communicate with each other.
So getting onto that scale issue, there's a lot of brilliant language in this space, and I did hear of a humongous fungus. How big was the humongous fungus?
So the humongous fungus is actually a pathogen. So it's a honey fungus, and it's in Oregon, isn't it?
It is in Oregon, yes.
Yeah, and it's I think it's 9 square miles or something like this. It's ridiculously huge, and this pathogenic fungus grows on tree roots and it attacks the trees, and it slowly moves out. But we think it's the biggest organism on the planet, or at least as far as we know.
That's as much as we're going to deal with the pathogenic funguses this evening, because we're really talking about all the potential that fungi have for us. Oh, you've got me saying fungi now. So it's spreading. Gavin, your company, Ecovative, uses fungal mycelium to solve problems. What qualities make fungi versatile enough to replace materials as diverse as cardboard and leather and plastics and wood and bricks and even meat?
Yeah, certainly. So fungi have some number of really interesting characteristics. So we as humans have been exploiting things such as plants and animals for a very long time for our material needs. Trees for our homes and other materials such as textiles, animals for their meat, and of course for leather. What's really unique about fungi, however, is that within nature they do serve a number of roles. They can be mycorrhizal, having these mutualistic relationships with other plants. They can also be parasitic, but the way that we really leverage fungi is as saprophytes, as nature's decomposers or recycling system. So what's really advantageous about fungi is they can take advantage of any type of lignocellulosic waste. This can be waste from agriculture, it could be the biomass that comes from trees, and they can convert those materials into the mushrooms you may see growing along the forest floor on the side of a tree. But what we're truly interested in is the fungal mycelium, or the vegetative tissue of the mushroom, which is truly gluing that mushroom on the side of the tree. Fungi are also composed of the same biochemical backbone that you find in lobster and crab shells. Chitin, which is the second most abundant biopolymer on our planet today, which makes them incredibly tenacious, as well as water insoluble, providing a number of different mechanical attributes that set itself apart from conventional materials that we use in our everyday lives.
So this is why we've started to hear about plastics made from, say, prawn shells.
Very much so, and
Right.
I do think that some of the world's most pressing problems, particularly that are based on our dependency of fossil fuel resources, either natural gas or petroleum, where a number of our plastic materials come from, has to be solved from an eclectic mix of biomaterials. It's not just going to be one solution. Fungal materials help support things like alternatives to conventional plastic foams, but it is going to be a mix of materials that really gets us beyond our addiction to petrol.
Right, so there's a very interesting symbiotic, you might say, relationship going on between you two. In that on one side, you've got this really micro interest in the materials side of what the funguses can offer us. And then on this side, we've got the symbiotic systems research. So Brian, I wanted to unpack this a little bit more because I'm not sure I still understand yet. What is the significance of the mycorrhiza, kind of the bioconnectivity? And what does that tell us about our world or how we might solve problems?
Sure. So most of my research is in forestry and forest regeneration. And essentially what we're trying to do is move away from this idea of we take the tree, and it's only the tree that we care about, and we stick it out in the environment and plant lots of them, and then hopefully we'll get a forest at the end of the day. That's not actually how forest ecosystems proceed. And what we're trying to do is think about the natural symbioses that plants are always interacting with when they're growing, and incorporating those into how we go about doing forestry operations. So it's really about trying to leverage natural processes. There's so much replanting that needs to be done. For example, the work that I'm doing in the UK now, UK governments have successively set targets for how much of the country should be reforested, and those targets have successively not been met.
I love it. So you're at both ends of the spectrum, really, with trying to solve problems and in a very green way. At one end, making sure that the plant life is really healthy and how funguses can help with that, and at the other end, how we can solve some problems with the products of that. Could we have a bit of an investigation of some of this packaging material we have here?
Oh, certainly. So this is what we call mushroom protective packaging, aptly named because it is composed principally of fungal mycelium, of a known edible mushroom species. And what it's composed of is, for us, locally sourced agricultural residue. So in the US, we grow a lot of corn, and what's important here is we don't use food-grade resources. We principally focus on agricultural residue. Those are the materials that cannot be fed to animals, and we as humans do not eat. But they're a great nutrition source for the fungus. So within our process, we take those agricultural waste streams, we mix them together with very trace or minute amount of fungal mycelium, and over the course of just 4 days, the mycelium actually digests some of these particles while binding the rest of it together. And what's really great about this is that all of the energy for growth comes from the agricultural waste. It's a set and forget process. And 4 days later, you can come back, we dry it to make sure that it's biologically inactive. That's our nice way of saying that it's dead. And then it can serve as a drop-in replacement for the conventional plastic foams. But the real value is, especially for these non-durable applications like packaging, is that at the end of its useful life, it can passively return to the earth. You can put this in plant-based compost pile, and it'll return to the planet in just 45 days, actively amending your soil.
So do fungal mycelium, you've mentioned the biodegradability, do they have any other particular qualities that make them particularly well suited to industrial processes?
Yeah, so first, in terms of industrial processes, we've used fungi for industrial processes like brewing beer or making penicillin, which is derived from the mold species Penicillium, aptly named there. And what's really nice about fungi is that they grow at an exponential growth curve. 1 cell becomes 2 cells, becomes 4 cells, becomes 8 cells, so on and so forth. It's quite stunning. So it actually fits within a time scale that we're used to from a manufacturing environment. The other thing that sets it apart from conventional plastics is its heat tolerance. Because it's not made out of conventional petrochemicals, it actually doesn't have a melting temperature until about 290 degrees Celsius, which makes it really ideal for a number of building and construction applications where you need to protect a home or protect multiple residences from the spread of a fire.
Brian, do you want to weigh in on this? Do you think that there are any qualities of fungal mycelium that have untapped potential?
Yeah, in fact, it's been really great to meet Gavin because we've had some wonderful conversations about how we can do some research together. Does anybody in the audience know what most of the money on tree planting in the UK, and I believe it's true in Australia as well, is spent on?
A few shakes of the head.
Plastic tubing to protect the seedlings. So if we can start to use fungal mycelium to do that instead, then you have a natural compound that will break down and provide nutrients for your trees later on as well. So there's loads of potential.
And you start to close the cycle.
Yeah.
That's beautiful. So Gavin, you answered this a little bit, but I want to check, are any of your products still in a living state as an end product? Could there be a use that you can think of where you would do that?
So most of our materials are sold today, all of our materials that are sold today are bioinactive in their finished product. But in order to allow others to engage in mycelium materials, we actually offer a grow-it-yourself kit, which allows both makers and designers, as well as small businesses, to grow their own mycelium products. So we have partners that range from growing surfboards in Southern California to lighting fixtures and other decorative elements in New York City. But I think one of the areas that we're most excited about right now is actually bioactive homes. So today, when we use building construction materials like trees, when we cut them down and we dry them, we're taking away one of the principal advantages of life forms, which is their ability to self-repair. And we think that it would be really interesting if not only you could have a home that could self-repair after there was some initial damage, say after a natural disaster like a hurricane, but also what if you could take a small portion of your house and use it to seed your neighbor's house and grow another structure in just 14 days. And so we've demonstrated this through what we call our mushroom tiny house, where we grew a small building, just a few square meters, and put it on the back of a trailer, because that's how you can not have to meet building codes in New York State. So that was key number one. And we were able to grow these small scale structures in just a couple of weeks.
Wow. You're blowing my tiny little mind. I thought I'd researched the hell out of this, but that was beyond. So let's talk more about manufacturing. As the ecologist, Brian, in what ways do you think industries are yet to apply the results of the research in your field? Do you think that there are elements, I guess in the pre-logging process most obviously, but are there more esoteric things that you can think of?
Oh, you're putting me on the spot there. I can certainly see all the applications in forestry. For example, when you're growing seedlings in forestry, one of the ways that demand is met, for example, in places like British Columbia, where there's a huge forest industry, is you grow your little seeds in polystyrene containers. So you have loads and loads of polystyrene containers that you grow your seedlings in, and then at the end of the day, what do? Can't really do anything with them. Maybe you could grow them in mycelium instead.
That sounds pretty great. Gavin, I want to ask, you've already gotten to mycelium-based homes. Is it true that while bootstrapping your company, at one stage you were cultivating fungi under your bed?
And in my closet.
Well, the closet seems natural.
Unbeknownst to my girlfriend at the time, yeah. It's true. So when Evan and I started the company, this technology came out of our senior design capstone at Rensselaer Polytechnic Institute as undergraduates in mechanical engineering and product design. And we had this wonderful professor named Bert Swerzy, and he really challenged us not to do nonsense. He was tired of engineers just going off into the defense sector and doing things that really harmed the planet rather than ended up benefiting society. So one of the things he challenged us with was to go out and find one of the world's most pressing problems, which we identified: the abundance of plastic foams used in construction, packaging, automotive components everywhere. And as two engineers, we were relatively naive about biology. We hadn't actually taken a biology course within our 4 years at university. And so we just read a couple of books, sourced some raw materials off the internet at the time. I think at that point in time we were using Pleurotus austratus, the common tree oyster, as our mycelium strain, but we didn't have any incubation vessels. So what we used were the darkest, coolest spots that we had in our apartments, which happened to be under our beds and in our closets.
That is a horror story. So for many of us, the first times we think of growing mushrooms in our homes, you'll grow your own mushroom boxes, or there's some sort of composting solution that involves a bit of fungus going on. Are there any other types of domestic solutions that are out there powered by mycelium or funguses?
Oh, well, I think Brian could certainly speak to this because, at least in the United States, you cannot find a potting mix that doesn't include some degree of mycorrhizal fungi. It's a real marketing advantage,
Yeah, very true. There's a lot of interest in incorporating mycorrhizal fungi, for example, into gardens. We always get asked, is there some mycorrhizal inoculum that I can use with my plants in my garden?
So that means they're actually looking for the targeted which fungus will specifically help these types of plants.
Yeah. What should I use with which plants? There's a lot of interest now in farming as well. One of the problems with the types of industrial agriculture that we're so used to now is that it completely chews up and disturbs the soil. And that, of course, chews up and destroys the network of mycorrhizal fungi. And so you start to get a system where you're losing all the natural symbioses, and you're not getting that additional uptake of nutrients from the soil. So we're hopeful that there are applications in agriculture as well. There's a lot of interest in no-till agriculture, and trying to move away from these very soil-destructive agricultural methods. And there's a lot of interest from farmers in this.
Fantastic. So we've talked about the growth side. I wonder, have you discovered any organic constraints when working with mycelium? What are your limitations in terms of how far you can go?
Yeah, so for us at Ecovative, one of the limitations that we found was initially the scale of the parts that we could grow. Because the fungal species that we work with are facultative aerobes, meaning that they consume oxygen and they respire carbon dioxide. So we found a geometric limitation of about 20 centimeters in terms of total depth before the material goes anoxic. It can no longer breathe, which can give way to contaminants like bacteria that smell like baby diapers, which is not a lot of fun. So one of the pieces of technology that our brilliant team came up with, and we have an amazing team at Ecovative, is what they call an aerated bed reactor. So in order to grow really large blocks of mycelium materials, you have to do two things. One, you have to blow air through it in order to eliminate or remove some of that carbon dioxide and replenish the oxygen. But fungi also give off a tremendous amount of heat when they're growing. It's about a single watt per every kilogram of material growing. So much so that in the winter months, which it's winter right now in New York, we heat part of our building with our fungal biomass. It gives off that much heat. And if you have too much heat, you actually end up differentiating the tissue too much. So by creating this particular system, blowing air through the reactor, we've been able to grow 1 cubic meter and beyond blocks, which then can go into industrial construction applications like acoustic panels and insulation.
Incredible. So the list of companies you're collaborating with is very impressive, from Dell and IKEA to Stella McCartney through Bolt Threads and MoMA in New York City. What aspects of your products are appealing to them most, do you think?
So from the very early days of Ecovative, the first and foremost thing that gets prospective customers across the finish line for us is actually not the sustainability component of it. What we found very early on is that it's not sufficient to have a sustainable story to sell a product. It doesn't really open the pocketbooks for many people, but it's really additional performance attributes, be it flame retardants as an example, or natural moisture resistance, but then also the economic competitiveness. So today, all of the materials that we currently produce serve as direct economic substitutions and actually have some performance advantage against the incumbent that they're displacing, be it plastic foams or bovine leather.
Wow, so as well as the social responsibility side, you've actually nailed the cost.
I'd love if a company came to us and said, we really want to partner with you because of the social responsibility, but that doesn't tend to be the case.
Interesting. Brian, we've seen really rapid growth in health sensor technologies as they've become cheaper and smaller and more sensitive. And I really kept thinking about your mycelium networks when I thought about this, because really they seem to be this vast system of sensors, just organic sensors. Do you think that we could expect similar growth in the application of bio-networks to give us the ability to track the health of plants or do anything clever like that?
I would love to see some research in that area. I think there's a lot of potential there. The thing about working with fungal networks in the soil is that working with anything in the soil is incredibly difficult. You spend most of your time working with an organism. You can't see it for most of its life cycle. Those little mushrooms that you see in the forest, that's just an ephemeral part of their lifestyle. Many fungi don't even produce those sporocarps above ground. And Australia has this huge diversity of truffles, which don't even produce spores to pop them out. They stay within the truffle, and hopefully a marsupial comes along and eats it and moves it around. So yeah, these systems are incredibly complex. They're linking up vast numbers of plants below ground. There's all sorts of things that are being transferred around by them. but they're just difficult to work with and see. So it would be really nice to look into different technologies that would help us with trying to do that sort of research. And I know that now there are some funding streams coming online, all to do with sensing signals in the soil. So hopefully, give us a couple of years, and maybe we'll be able to get some technology that will help to solve that problem.
Fantastic. And another area that was uncovered in my research, which was something I wasn't aware that you could do with mushrooms, was that I discovered the concept of a mushroom circuit, like an electrical type of circuit. Could you explain what a mushroom circuit is?
Oh, certainly. So this is derivative work that came out of Montana. In Butte, Montana, there were some professors that were exploring the use of fungi to actually remove heavy metals from water. Because fungal species are really good at what's known as biosorption. They can accumulate various metal salts onto the exterior of their cell wall. Things like gold, aluminum, copper, some very common water contaminants, especially around mines. What wasn't explored, however, was what happened to the material properties or the mechanical properties of the materials after they were grown. And one of the things that we discovered is that first, the fungal cell wall, which is chitinous again, is inherently dielectric, meaning it's an electrical insulator. It doesn't allow electrical conductivity or to permit through. But when you grow it on these various types of media that contain high salts of high concentrations of copper or aluminum, as an example, you can actually modulate the conductivity or resistivity of the tissue, in essence creating a mycelium circuit.
Yeah. And the example I saw of this posited the concept of a mushroom-created torch type thing. So this fungus actually would light up. Have you seen anything like that in your work?
Well, I am familiar with some bioluminescence in fungi.
Yeah.
And I'm certainly not a mycologist. I'm a mechanical engineer by training, so I'll punt that one to Brian.
Yeah.
I haven't seen lighting up mushrooms, unfortunately.
Right.
There are
I'm
some
trying to
bioluminescent
understand.
mushrooms,
Yeah.
but this is a new one for
See,
both
the
of us,
internet
I
and
think.
special effects, nothing can be believed. Nothing can be believed. So what potential do fungi have to be part of a reduction of waste products? We've got your packaging type things, and it's very clear to us immediately the applications replacing plastics there, for example. But do you think that there are other examples we probably haven't thought of?
Sure. So fungi, as mentioned, are wonderful at picking up heavy metals, and the concept of fungi for bioremediation isn't an unknown one, but I think there's a lot more room for considering how to use that most appropriately.
Yeah, from our side, one of the areas that we see an abundance of waste is in animal agriculture. Animals are actually very biologically inefficient. We feed them lots of grain. If they're fortunate, they eat grass like they're supposed to, but they're very poor at converting those plant-based materials into cow. They're typically about less than 1% biological efficiency. So one of the things that we're presently exploring is how do we eliminate the greenhouse gases associated with animal agriculture? And one way that we're looking at that is growing large sheets of mushrooms, but not in the shape of mushrooms, to create materials that have meat-like textures and flavors, but are not derived from animals.
That's exciting to me as someone who's had to make mock meats in a very Asian style, and it requires a lot of kneading. If you can just grow this out of a fungus.
Well, that's right. So a lot of the alternative protein sources that are used for meat are in the ground meat form. They're in burgers or in sausage. But really, the things that we like in terms of meat today is the texture. And fungi are really good at laying down these very oriented fiber structures that provide very similar to alignment to the myocytes or the muscle cells that you would see in animal tissue. And of course, we've been using mushrooms as meat alternatives for a really long time, but they're always in the shape of mushrooms.
That's amazing. Brian, do you think that there are many unanswered questions in mycology, and do you have plans to explore any of them?
There are loads of unanswered questions in mycology. One of the great things about coming here and doing the Planet Talks and this talk tonight is just seeing how much interest there is in fungi. I think it's astounding. You know, there aren't all that many mycologists around anymore. I believe there's a a genuine mycologist in the audience, though. There's, as far as we know, there's one official mycologist in Australia.
And he's here.
Yeah.
Can you pick
That's
the
the
mycologist?
rumour
This is a bit of
anyway.
a Where's Wally situation.
That's
I don't
good.
think we can
Hopefully-
recognise a mycologist.
Hopefully in a few years, you'll all be mycologists,
There
because
you
you'll
go.
all be thinking about fungi at least.
Career options.
Yeah, in terms of what we can do with fungi, I think now that people are actually starting to take an interest in them, the sky's the limit.
That is very exciting. Let's go to ethical considerations. I guess we touched on them a little bit. Getting into that, meat replacement territory is very interesting. Are there any new ethical considerations in terms of interacting with plants that have come out of your research, Brian? Do you think about them differently?
I think there's been a lot of interest in that aspect of the research, as much as in the actual science behind it. And we've had some really interesting conversations about the ethical consequences. I think the important thing is to realize that to eat, we have to eat living organisms. And does it really matter which organisms they are? Is that supposed to determine how we treat the natural world? So I guess if people are thinking about plants and fungi communicating, maybe it's giving them another in to thinking about the natural world and maybe taking better care of it.
But then my carrot is not screaming as I eat it. It's in a what did you call that non-living state of things?
Inactive.
Inactive. My carrot, once plucked from the ground, would be inactive.
Yeah, your carrot is no more.
Therefore ethical.
It's an ex-carrot.
Excellent. Excellent. I'm glad to hear that. Let's discuss the biodegradable qualities of fungi. Is there anything that you could do to a product made out of fungi that would render it non-biodegradable?
When it comes to the biodegradability, it's really important to consider the environment. So the wood that is used to construct your house is also biodegradable, but it's in an environment in which the certain soil microbes do not reside in order to break those materials down. And the same is true for these materials. So for example, we do not recommend putting these materials in the dirt for any building and construction applications. And oftentimes insulation does go below grade. So it's not a good fit for these materials. And similarly, you'd use concrete or other types of agents rather than wood, or they'd be pressure treated with things like arsenic or copper, right, which isn't desirable. But what's key is that these materials are compostable, but so is a log that you'd see in a forest. And a log will sit in the forest for a prolonged period of time because of its shape and its structure. But if you were to take that same log, chip it up into small pieces, it'll more rapidly biodegrade. And the same is true with these materials.
That's great. All the benefits that we're familiar with. So are there any regulatory barriers, do you think, to widespread adoption of fungi-based materials?
Oh, certainly, and being here in Australia certainly brings those to light. And part of what's important about this material platform and paradigm is that it really requires a regional model. We don't want to be shipping lightweight materials across the world. The intention is to take advantage of local resources and local mycelium strains that have adapted for individual climates and regions and territories. So part of the reason why I am here in Australia for the next few weeks is I'm starting to begin to build additional relationships here in Australia with mushroom farms and other companies that want to bring mycelium materials to Australia.
Brian, I wonder, are there any other problems that you suspect might be solved with mycelium which haven't been cracked yet?
Oh, that's a really great question. Well, other than their use in building materials, there's a lot of interest in fungi and potentially mycelium in health sciences. It's another untapped resource there. We tend to think about fungi and health sciences in terms of antibiotics. That's where most of our good antibiotics are still come from fungi, but perhaps in bioengineering. And
is it the things like the exponential growth qualities that are particularly good, or is it its ability to hold onto nutrients and sort of carry other things? Like what are the qualities in particular that
Well, you can
could
grow
tap
them
more.
into all sorts of different shapes,
Yeah.
like Gavin has discovered with Ecovative. You can get mycelium to grow. If you give it a mold in the right shape, then it will grow into that form. So there, you can see there's loads of potential there.
So much better for the environment than most of the 3D printing that we're seeing lately.
Yeah. We're actually doing some interesting things in that space for the biomedical industry. So one of the interesting things that is starting to occur in the biomedical space is tissue engineering, where various scientists around the world are starting to grow mammalian, particularly human tissues, so that we could grow alternatives for things like bone or other organs. So if I were to need a new liver in the future, perhaps that could be grown. But mammalian tissue also requires structure. And normally in the body, it creates its own, what's known as extracellular matrix, or proteins as a scaffolding to grow. But when you're growing these cell lines outside of the body, they still need structure. And so one of the things that we began to explore with some scientists out of the University of Ottawa in Canada is using mycelium as that natural scaffolding, because it is biocompatible and compostable, to serve as the structure to grow tissue on. And to date, we've been able to demonstrate that we can grow human bone tissue right on fungal mycelium, have it fully mineralize, and as Brian mentioned, have it grown to shape such that you can potentially, and this is something we see in 3 to 5 years, not tomorrow, actually have something that's compatible with your body and implantable.
Wow, that is very impressive. I hope I'm not the only person in the room whose mind went to that Franken mouse with the ear on its back when you were talking about this and thinking, will we see an ear growing on the top of a mushroom? That's what I'm visualising. That's very exciting. Brian, has your research fundamentally changed the way you look at nature?
Good question. I think if you're working in ecology, then your research always changes the way you fundamentally look at nature. Certainly, I came into working with plants and fungi starting out as a wildlife management student, realizing that not only were the habitats of the creatures I was working with super important, but they were less likely to move around when I was trying to study them. So I kind of moved from animals to plants and then below ground to all the symbioses that the plants are involved in. And it's really coming full circle. You really start to appreciate all of these interconnections and the layers of complexity in the natural world as soon as you start to try working with fungi and soils. It really becomes quite clear.
I will be opening up to the audience for questions very soon, so please put your thinking caps on and get something ready for these experts. I wonder, can Australians see any Ecovative products here in action yet?
So we're currently not selling materials within the Australian market. We do export finished goods because they're heat treated, very similar to wooden pallets that might be imported into the country. But unfortunately, we cannot offer our grow-it-yourself kits, which we've received a lot of demand for. But we do think that there's a vast opportunity to build initial supply chain relationships with mushroom farms, because they have all the expertise that you need to produce those raw materials, and to start partnering with organizations that want to start growing their own mushroom packaging and perhaps even building construction materials. So coming soon to an Australia near you.
Very good. Brian, what would you want people to learn from your work if they could just take one thing from your research to date?
Just to think about the connectivity of living ecosystems. When you see a tree, remember, it's not just a plant. It's the process of all the interactions that plant has gone through, from being a seed, interacting with bacteria, interacting with fungi, interacting with animals, and it continues to grow and change and interact with all of these different organisms. So try and think more about all that interconnection that's going on that you can't see, you don't typically think about it, but the next time you're walking past a tree, just remember that.
Gee, it's very timely to be thinking about the connectedness and rethinking our processes. It's time for us to throw to you. There are a couple of lovely people with microphones here who will look for you. and choose people who they'd like.
Fabulous talk. I was wondering whether there's any possibility that the fungi might come to the rescue with the world's big plastic problem. They're a great bioabsorber, but can they help us turn plastics into something less toxic?
So fungi are really interesting in the fact that they produce this wide range of enzymes. And some of them are known as isoenzymes, meaning that they're very complex and can cleave really large molecules like plastics. So one of the biopolymers that fungi go after is what's known as lignin, and it's an aromatic or cyclic carbon source. And that's the same structure that you find in a lot of plastics. So there's been some amazing research that's come out, particularly out of Tom Volk's lab in the University of Wisconsin, where he's used a common white rot species, a fungus that particularly targets lignin, to degrade plastics, such as polypropylene. So there is a potential to bioremediate or to degrade plastics using fungi. But from our perspective, it's best that you just don't create those plastics in the first place.
Yeah, hi. So I've heard that suggested that fungi can be used as a carbon capture and storage type mechanism, and I've heard on the other hand that it can't be because it is quite fragile and easily broken down, and it's not in the soil. It's not terribly heat. You know, if you have a bushfire or something else, it'll die and release all that carbon back into the atmosphere, so it's just not stable enough. What's your thoughts about using fungi on a kind of a large scale as a kind of a carbon capture and storage mechanism?
Yeah, thanks for that question. So in forestry, when you're growing trees, they're interacting with the fungi in the soil, and a lot of the carbon that the tree is photosynthesizing is actually going to feed those mutualists. And what tends to happen is that carbon that gets transferred to the fungi, because it's buried in the soil, it actually decomposes at a slower rate. So you get the transfer of the carbon into different soil layers. Some of these fungi can actually be quite deep down in the soil. And so the biomass starts to accumulate down there. It doesn't break up as quickly as it would if it was at the surface. And so you get this natural store of carbon that's turning over more slowly, that's connected to the trees. So you get the double whammy of growing trees that are sequestering carbon, but they're also passing some of that carbon to other organisms in the soil. And yes, some of it will turn over and be respired, but actually quite a lot of it will be stored in the soil as fungal biomass.
With a design background, I'm interested in building materials, and the application, it seems to me, would need to be in combination with other materials. And the one that really comes to mind that's very topical at the moment is this aluminium sandwich material, where the core has caused these terrible fires. And so I'm wondering what manufacturing techniques you can see perhaps in the future that will combine the use of this material for building elements with other materials.
Yeah, certainly. So the structural sandwich construction you're discussing are structural insulating panels, where you normally use a stress skin or something that's very stiff on the exterior of what's normally foam insulation. And that was precisely the challenge, is that heat rises and will travel. And especially if you have a chimney where you have air moving over the building construction envelope, which we all do because wind is fastest at higher heights and elevations, is that it really can help carry that fire up through those foam insulation panel boards. So for us, we have explored structural insulating panels as a particular a market as well as a construction envelope to explore. The thing about mycelium materials like these to think about is that mycelium is naturally an open cell foam, meaning that it does allow some breathability or water vapor transport. So normally we pair these materials with water vapor barriers that go on the exterior face of the panels, which do not permit liquid water from hitting or going into the material, but allow gaseous vapor transmitting through, and that's really important. So the construction applications that we currently serve today include interior applications for acoustics. So for example, if you were to say within this built environment, the frequencies that we'll typically experience are between 0 and about 8,000 hertz. And the mycelium materials, because of their open cell structure, will actually absorb about 90% of that sound that's bouncing around within this room. In the insulation space, the materials have been qualified for exterior insulation with a weather barrier, what's known as exterior insulation and facing systems. So there's normally either a mineral facing agent or a plastic weather barrier that helps prevent the liquid water from permeating in. And then also structural insulating panels, because the materials provide excellent compressive strength, where the exterior tensile panels and skins provide great tensile strength. So collectively, you get a great racking strength performance, which you can use to build and construct homes. And we've done this quite a few times, mostly in Europe. So there's a Dutch foundation that's a partner of ours, the Dune Foundation, and their most recent headquarters in Amsterdam is actually composed of structural insulating panels made with mycelium on their top 2 floors.
More strength to your arm.
Yeah, hi. I was just wondering, I imagine all fungi are not created equal. So I'm interested in what work's been done to create new species of mushroom and what that kind of means.
Any idea, Gavin?
Well, from a materials perspective, you're right in terms of, well, all fungi are wonderful, but their physical properties are not all the same. So the species that we typically focus on are those that you might find growing on trees. And they produce 3 different types of hyphae, which are collectively known as mycelium, but individual strands are known as hyphae. And the ones that we focus on produce what are known as skeletal and binding hyphae, because they have really thick cell walls, which make them far more robust. You're basically putting down all of these little cylinders, which have a great, from a mechanical perspective, moment of inertia. They're super stiff and strong. The other thing that we're looking at is not just how we can engineer fungal species, which we do have a molecular biology and genetic engineering program in-house at Ecovative, but we're also looking at how we can cohabitate other organisms with our mycelium in the composite matrix. Because we as humans have looked at monocultures for a really long time, but life doesn't grow in a monoculture. And we thought that we really needed an industrial microbiome. So how do we take advantage of other soil bacteria, like Bacillus thuringiensis as an example, which is a very common soil bacterium, and use that to help inhibit other bacteria in the mix so that we can reduce our pasteurization and sterilization energy. So yes, we are targeting very specific mycelium species, and we're taking that a step beyond to say, how can we take a look at the rest of the microbial community and create the industrial microbiome?
Hi, thanks very much. Look, I'm a mushroom farmer, so I'm very interested in what role the traditional and non-traditional mushroom farms can play, particularly around the waste product. And the main waste product of my farm is living mycelium, is living mushroom that is, has fruited and produced mushrooms that we've harvested. But it's still going. It's still there, and basically it just sits in a compost pile and composts. From both an environmental perspective in terms of what can be used in the forestry, and also from a materials perspective, what opportunities might there be?
Well, fungal biomass is great for the nutrient content. So using it in perhaps in conjunction with tree planting to provide some more nutrients for seedlings when they're going in. The hardest part for a plant is usually, well, actually the point from going from a seed to becoming a seedling. That's where most of them die off. But then as seedlings, trying to grow beyond that. So potentially there would be uses in integrating mycelium into mixes that you plant with your trees when they go into the ground.
Yeah, because fungal mycelium is rich in nitrogen, because of that chitin backbone. So it's a great soil amendment for that reason. And then it really depends on the mushroom species that you're growing. So come connect with me after the talk and we'll chat a bit more.
So, look at those supply chain opportunities just cropping up before our eyes.
I was interested in the implications. I work at the University of Melbourne, and the implications for educating the creators of the sustainable society of the future. You started saying you were an engineer who knew no biology. Is there transformation happening in universities around the way we educate the engineers to create new interdisciplinary syntheses, to imagine new kinds of ways of creating building materials, pharmaceuticals, etc., using living materials?
Certainly. I think it's important to consider that nature as an engineer is really an opportunist, not a perfectionist, where we as humans try to value engineer everything to be the most cost competitive and last for the least amount of time possible. Life doesn't do that. Life is really durable. And what we're seeing is a large growth in the biofabrication field. And there's a gentleman by the name of Mike Hornblow, who we were on a panel with just a couple days ago, who's leading a class in architecture and design in biofabrication strategies. So these are things looking at marine alga and or any marine alga and how it could be used for things like flatware and dishes because of its rapidly renewable biomass source, or how we can use things like SCOBY, the mother culture that grows on top of your kombucha. We have differing opinions on that. To create unique things like textiles, and there's some really interesting work out there. So I do think that we're starting to see a bit more of a perspective in the engineering and design community starting to look at bioactivity opposed to biomimicry. And I think from the early 90s to now, there's been a real focus on biomimicry. How can we take nature's structures and replicate them using our common man-made methods? And what I think separates biomimicry from biofabrication, what I know it separates, is that biofabrication is actual biology. So now you're really starting to leverage ecological systems.
And for my part, for a slightly different take on interacting with engineers, I'm doing some work with engineers in the built environment, and we're looking at trees in the urban environment and getting engineers to think about what trees actually need to survive. I don't know if you're aware, but there's a large percentage of trees that get planted in urban areas that will die within about 10 to 15 years of being planted. Often we stick them in a little box, maybe a meter by a meter by a meter, and throw a tree down there and expect them to survive.
Right? Yeah.
Usually after throwing the tailings from a building site in there to get them going. You know, that's soil. So yeah, it's interesting working with engineers and getting people thinking about what do trees actually need? What does biology need? You know, we have trees in the built environment. We know that trees are good for their cooling properties, for making us feel better because they're around. But how can we actually start to incorporate trees into the built environment in a sensible way that benefits us and them?
This will probably be the last question, so you're lucky last over there.
I don't know if you're aware of the situation in Australia with the rabbits, for instance, that were introduced to make the climate much better for Europeans living in this isolated continent. Cane toads that were introduced in a similar way. My question relates to, is there any way for us to protect ourselves against introduced mycelium species because they're so easy to move around? And is there any need to do that? Are mycelium that are beneficial to a particular species of tree specific mycelium that are different from other mycelium? So is there any need to isolate ourselves?
Do you want to take that one first, Gavin, or shall I?
Yeah, why don't you go first, and then I'll hop in on the materials side.
All right, that sounds good. So I work a lot with these mycorrhizal fungi that form lots of hyphae and explore out in the soil environment. Now, most of the time I'm working with Douglas fir, but I've started working with lots of other species. You may know that eucalyptus is planted all over the world as a forestry species. Pine has been introduced all over the world as a forestry species. Why? Because much like the head of the Sydney Botanical Garden, who really liked rabbits and thought that they should be introduced to Australia to make the place a bit better, we like working with species that we are familiar with. So there was a lot of interest in the forest industry for moving eucalypts and pines around the world because most of the people who were foresters knew how to interact with those trees. And of course, that has had lots of unforeseen consequences. If you go to Hawaii, you can find pines growing, and you will also find the swillus mushrooms that were brought along in the soil that got those pines going in an environment that did not naturally have those fungi. So the issues surrounding introduced species are, I think, quite well known now, but we continue to introduce species into places where they wouldn't have naturally occurred. You've got the Phytophthora fungus, which is killing lots of eucalypts here. That's actually a different type of fungus altogether. But when we start moving things around, we really need to be very careful about what we're doing. And I think that's where what Gavin's doing is great, because he's trying to get people to use locally sourced materials. So instead of thinking, hey, I really like my mushroom in America, let's ship it over to Australia as quickly as we can and then deal with the problem later, it's all about actually using local solutions. So I'll pass that over to you now.
And that's exactly right. That's our principal focus, is not just trying to translate the same strain and species that grows exceptionally well in upstate New York, but to identify the species that have the same physiological characteristics, so how good are they as a natural or grown glue, have you, that are best fitted for this particular environment or any environment, as well as the raw material resources that surround them. So we have a really cool team, our strain development team, which is a cross team of a number of different scientists that work on various projects. And one of their goals as an organization and as a team is to actually go out into different environments where we're starting to foster partnerships. They have a really cool job. And say, for example, if we're working with, and this is a tree that we work with in Oregon, ponderosa pine, is to go out and find the fungus that grows really well on ponderosa pine, because it's far easier to pair the natural saprophyte that is existing within that environment rather than trying to train a fungus that is not well suited to grow on that particular species. So it is very focused on being local, and there's some inherent benefits about leveraging the fungal evolution that go along with industry.
Well, Dr. Brian Pickles, Gavin McIntyre, thank you so much for being our learned guest this evening. Thanks very much.
Visit wheelercentre.com for the best in books, writing and ideas from Melbourne, Australia and the world.